All right, so in this lesson, you're going to see what reflection and rotational symmetry is all about. And anytime you need Desmos, just click here and that'll take you straight to Desmos. But what we're going to talk about first is reflection symmetry, and then we'll talk about rotational symmetry. So for reflection symmetry, you have reflection with respect to a line. So you've seen snowflakes and where you fold them up and you start cutting and you open up and everything is symmetrical. So what you're looking for is if you can draw a line straight down the middle, straight across the middle, diagonal, and you can fold one corner directly onto the other. That's called mapping. So if I can take this right bottom corner and when I fold it along this dashed line here, it maps right on top of this diagonal corner here. And these two, of course, would fold onto each other. So this one has 1, 2, 3, 4 lines of reflection symmetry. So 4 lines of symmetry, so it does have reflection symmetry. Here is an X, and you can see this right side will flip right onto, fold perfectly, map onto the left side, or vice versa. So it says here that object can be drawn, a line can be drawn of the object such that when one side is flipped on the line, the object form is congruent to the original object, vice versa. So that means also if I use that line as a line of symmetry, I take this top part and I flip it to the bottom, I take the bottom and I flip it to the top. It doesn't even look like it has been flipped, okay? So that's what they're talking about here. So either you can fold it and it maps perfectly, you can think about it that way. Or if you just reflect it across one of those lines, then you can say, hey, I've got myself some reflection symmetry. All right, this one right here doesn't have reflection symmetry. So if I draw a line here, a horizontal line, you can tell that this side right here is larger than this side right here. So this little vertex here would end up way down here somewhere. Okay. All right, so here's some more examples of reflection symmetry. Okay, so here's a square. Remember what a square has, 4 sides are congruent. And you can see it also has 4 lines of symmetry. Here's a rectangle. I can take this top horizontal line and I can fold it and it will match up with this bottom horizontal line. Or I can say that I reflect across this horizontal line and this corner goes up here and this corner vertex goes down here. Same thing here. Here's a rhombus, which has all 4 sides are congruent here. There's a line this way. This vertex lines up with this vertex. So if I reflect it across this line of symmetry or reflection line, then this right side would flip over to the left side and the left side would flip to the right side and it would look like I didn't even flip it. Or you can say the right side does fold like a card that you've made for a relative, perfectly lining up to the left side. Here's a kite. Here is an isosceles trapezoid. Remember, isosceles means you have 2 congruent sides. That would be this side and this side. So right down the middle, the left and right side could fold like a card. This one doesn't have any lines of symmetry. Isosceles triangle right down the middle because the left and the right sides are congruent. So this vertex and this vertex would fold on top of each other. And here's an equilateral triangle with all the vertices one at a time flipping over. Or you can do diagonal. Here's a diagonal one right here. This one flips to this side here. All right, regular polygon. Regular right here means that all sides are congruent to each other and all angles are congruent. That's what regular means. So here's an example, a regular polygon. This is the number of lines of symmetry equals the number of sides that polygon actually has. So this being a pentagon, which has 5 sides, so it's going to have 5 lines of symmetry. 1, 2, 3, 4, 5. Okay, so real quick, here's some videos right here you can look at. Here is some cool notes on reflection symmetry here. You can see some everyday pictures. There's the line of reflection, the mirror line, the line of symmetry has multiple names. Okay, here's this one. Alrighty, here are some examples of pictures that are showing you perhaps maybe the reflection across the x-axis. If we pretend like this horizontal line is our x-axis, you can see the left and right side. If I fold them, they will literally fold. This tip of the tree will line up perfectly with this tip of the tree. This corner vertex here will line up perfectly with this vertex here. So you're folding the object like it is a Christmas card. There we go. You have a vertical line like the y-axis. Here's the line y equals x, a diagonal line. So this one has a diagonal line of symmetry. Here's another one. Here's the line y equals negative x. And once again, here's some triangles. Equilateral triangle has 3 lines of symmetry. Isosceles only has 1. And then you can go here for some practice. It says John notices that a standard piece of paper is a rectangle. How many lines of symmetry does it have? Well, remember, if it's a rectangle, you had a horizontal line of symmetry and you had a vertical line of symmetry. We just saw that on, I believe it was the assignment itself. Down at the bottom, there's a rectangle. So you have the horizontal line of symmetry and you have the vertical line of symmetry. So once again, you can go through these. So that would be 2. And this does a really good job of showing you the right answer and immediate feedback. So go ahead and do some practice there and read through those notes. All right, next we're going to talk about rotational symmetry. So rotation, of course, you know you're turning. Okay, another word for that is radial symmetry. So an object has rotational symmetry if it can map onto itself as it turns before it gets to 360 degree, before it gets all the way back to its start. Okay, and the order of the rotational symmetry is the number of times that it does in fact map onto itself as it does that one rotation all the way around. So the order of rotational symmetry tells you how many times it maps onto itself, and it has to be more than 1, okay, because 1 would be at the start to the finish is 1, and it has to be more than 1 to have rotational symmetry. Okay, let's see here. Let's see. Dun, 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 dun. Down at the bottom, this is a really good picture here. So if you take this object, excuse me, and you rotate this object, this is clockwise, how many times can it map onto itself? Okay, so this side here is congruent to this side, congruent to this side, and congruent to this side. These are all congruent edges. So if I turn it 1 turn, that was what it would look like here. If I turn it again, a second turn. So 1 turn would take this piece here, right to here. A second turn would take this piece here to here. A third turn would take this piece here to here. And a 4th turn would make the whole complete 360 degrees. So that has an order of 4. From start to finish, from the first turn to the last turn to end the 360 degrees, you count the number of times that it mapped onto itself. So 1 turn was 90 degrees, 180, 270, and 360. So that's called an order of 4. So it has a rotational symmetry of order 4. Then you'll be asked about magnitude or angle of rotation. To find the angle of rotation, that's these guys right here. 90 degrees. It is the smallest number of degrees that you will get on your first mapping. So you just take 360, which is your total complete rotation, and you divide by the order of rotation. So the order was 4, 360 divided by 4, 90 degrees is the smallest turn that I would be able to accomplish a mapping. All right, so let's take a look at some examples. All right, so this is rotational symmetry. This was really, really fun here. So it shows you how it's rotating. Let's start this one over. Okay, so here we go. We got the first one, which is an S shape. So it's showing you it's rotating 1 turn, 2. So it has 1 complete turn, but it stopped at 1 and then at its end. So that's called an order of 2. So the first turn was a 180 degree turn. So there's 90, there's 180, and then it 360. So 360 divided by 2 is 180. 180 tells us the smallest angle of rotation. which is called the magnitude or just angle of rotation. Here's another one. This one has 3 congruent pieces to it, so you can watch it turn. Maps 1, maps 2, maps onto itself 3 times from start to finish. The first turn that it stops all the way to the 360-degree ending. You're counting how many times you can map. In this case, it's 3. Here's some more examples. This is the order of 2 we just saw. There's the order of 3 that we just saw. Here's the order of 4. So you can see how many congruent pieces you're looking at, and that will tell you how many, the order that you're going to see. This one has 8 pieces, so you're going to have an order of 8. Now to find that angle of magnitude, or the angle of rotation, you just divide that order into 360. Okay, and here's some more examples here. And you can click here. Okay, what is the order of rotation for a regular pentagon? Remember, a regular means all the sides are congruent. All the angles are congruent. Pentagon has 5 sides, so that would be 5. Now, the angle of rotation would be 360 degrees divided by that 5. So you take the 360 and you divide by 5, and that's how they get 72 for the angle of rotational symmetry. Here's a star. So this is asking how many times can it map onto itself. So you're looking at the red dots, the red triangles. So if I turn it to here, that's 1. If I turn it to here, that's 2. And if I get it back to its original spot, that's 3. So it has a order of 3. And if I want to know what the magnitude or the angle of rotational symmetry is, I take 360 and I divide by that 3. Okay, so that's how you get 120. 360 divided by 3 is 120, and that is the angle right there. Let's try another one. Here we go. So once again, you have the little blue corners we're talking about. So let's count how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So 9, I can take this guy and he'll go here once, then he'll go here 2, 3, 4, 5, 6, 7, 8, 9 to get him back to where he started. So 9 times he will map onto himself. So if I want to find that angle or magnitude of rotational symmetry, then I take 360 and I divide by that